Okay, you guys. I want to talk about the pH at the equivalence point when we're doing a weak acid, strong base calculation. So this is number 6 in your calculations for part 2. So we're going to start out exactly the same. We're going to find the moles of acid, we're going to find the moles of base, and then we're going to use an ice table to find what's left. The difference here then is how we find the pH. So I'm going to show you this process with my values. So when we calculate the pH at the equivalence point, the definition of the equivalence point is that the moles of acid are equal to the moles of base. Now, this is lab, so it's not totally perfect. You might have a small amount of acid or base left depending on how accurate your titration was. It's going to be such a small value that you can just ignore it for our purposes. So first thing we need to do, this is how you've been setting your other ones up, we need to find the moles of acid. Now, if you've already calculated the moles of acid for one of your trials, keep using that value because acid is what we delivered to our flask in the beginning. That one doesn't change. So for my trial, I used 2.01 milliliters of my acid, and I want to find moles. So I know that for every 1 liter, there's 1,000 milliliters. And then from my calculations, I know the molarity of my acid in this trial was 0.855 moles for every 1 liter of solution. So I know that in my flask, I started with 0.00172 moles of my acid. Okay. Then I delivered base to it. This is at the equivalence point. So this is the actual value of base that you used. So I delivered 17.10 milliliters. And I know that there's 1,000 milliliters in 1 milliliter. And then I made your base. So I know that it was 0.100 molar. 1 liter. So I delivered 0.00171 moles of base at my equivalence point. Okay, so this is initially what I had in my container. So I started with 0.00172 moles of my acid. I added 0.00171 moles of my base. And this is my conjugate base. So that's one of my products. I started with none of it. My change for this, it's a 1-to-1 reaction, which means that for every 1 acid, it reacted with 1 of my bases. So all of my base is going to react. And that much of my acid is also going to react. Now, this is also 1-to-1 with my product. So that means that that is how much of my conjugate base I'm going to form. Okay, so I'm going to do my at equilibrium calculations. I'm going to end up here with 0.00001 moles of my weak acid. That's not going to do anything. So I can kind of ignore that. I'm going to say that that's about 0. My NaOH really is 0. And then I have 0.00171 moles of my base left. So you guys, at this point, the only thing that's in my container is water and conjugate base. So I'm going to expect that this is a basic solution. I've used up all of my acid at this point. My conjugate base is a rather weak base, so I'm going to expect that it will be above 7 basic, but not too high above 7. So I'm going to do this calculation now. Okay, so we'll remember those values. We are going to set up the next part. So this is actually what's happening in our beaker. We've got our conjugate base here, and it's in water. So what's happening is basically a dissociation equilibrium problem. It's acting as a base. My water is acting as an acid. And I'm creating a little bit more of that acid back. So I'm kind of creating a little bit of that acetic acid. And then my hydroxide ions, which is going to be my conjugate base. Now I'm doing a weak base problem. So I need to write my Kb expression. So KB is going to be equal to my products over my reactants. And I'm not including water because it's a liquid. I know my concentration of my CH3COO minus. I just calculated that. So I know that that is 0.00171 moles. But in order to use in this equation, the brackets mean concentration. So I need to divide that by the total volume of my solution. So the volume of my solution, I added 2.01 milliliters of my acid, and then I added 17.1 milliliters of my base. And then remember, you guys, we also added 20 milliliters of water. And so our entire solution is 39.11 milliliters, but we want it in liters, so it's 0.03911 liters. And again, we have to do this, we have to get it back to molarity in order to use the KB expression. Okay. I know the Ka of my solution, my Ka, was 1.8 times 10 to the negative fifth. I also know that Kw is equal to 1.0 times 10 to the negative 14th. And that's equal to my Ka times my Kb. So if I know my Ka value, I can calculate Kb. So the Kb of my acetic acid is going to be 5.6 times 10 to the negative 10th. Okay, so I know down here, I'm going back to my equation, 5.6 times 10 to the negative 10th. Now I don't know anything about these products, or do I? This is all a molar ratio of 1. So I know that every 1 hydroxide I make, I'm also going to make 1 of the acetic acid. So those are the same, but they're unknown. So I'm going to give that an x squared value. So what I want to do now is rearrange for my x. So when I solve for that with my values, I get 4.9 times 10 to the negative 6, and that's equal to my hydroxide. Okay. Now that I have my hydroxide value, I can find my POH. So my POH is going to be the negative log of that 4.9 times 10 to the negative 6. But I've been calculating pH along the way, so this value isn't super helpful. So pH is going to be equal to 14 minus 5.3. And that gives me a value of 8.7. Okay, so at the equivalence point, I have conjugate base, and I have a pH of 8.7. So that means it's slightly basic. That totally makes sense to me. So remember, you guys, in the weak acid strong base titration, the strong base kind of wins even at the equivalence point. And so my whole titration curve is pushed up. I start at a higher pH because it's a weaker acid. My equivalence point is higher. It's actually basic. And now when you do the next calculation, when you do 2 milliliters after, you're going to have a ton of excess hydroxide ions from your sodium hydroxide. It's going to be super basic. Okay. Once you have all of those points, you're going to have your initial pH, your pH at the half equivalence point, your pH 2 milliliters before, at the equivalence point, and 2 milliliters after. You have 5 points for your graph. Put those into your graph, connect your dots, and you should have a really nice titration curve for this problem.